Hello and welcome to another review session for the final exam in Calculus 3208 presented by CDLI. And today what we're looking at are some further applications of derivatives, and we're still talking about all the details that we can get about graphs and curve sketching. And what we're doing this time is we're using the second derivative involved with that stuff. So we're looking at the second derivative to determine concavity and inflection. So those are both things that we've talked about before, concavity and inflection. But what we're going to do is we're going to put a lot of the details in there today in terms of how we would do that for specific functions instead of just generally. Okay, so we're going to find inflection points and other possible concavity changes, and we're going to determine intervals of upward and downward concavity. So where we're concave up and concave down. So an inflection point is defined as any point where the concavity changes for the graph. So if we shift from being concave up to concave down, or if we shift from being concave down to concave up. So that would be an inflection. But to actually be an inflection point, the one more stipulation we have to say, so there's where we shift concavity. So a place like this, from concave up to concave down, or like that. Those are what typical inflection points look like, points like that. But it says in order for those to get there, we have to be continuous. If it's going to be called an inflection point, we have to be continuous at x equals a. So it can't be a graph, for instance, if I have an example here, just a graph with a vertical asymptote where we're going this way, so we're concave one way there, and then we could be concave the other way on the other side of that vertical asymptote. That vertical asymptote, we do have a change in inflection there, but it's not technically considered to be an inflection point. We'll talk about what that means in a second. Okay, once we determine where all these possible changes in concavity can be by looking at our second derivative, then what we do is we do what's called a concavity test. And the concavity test basically should go right back to stuff that we did when we were comparing graphs of derivatives and other functions together. So on any closed interval a to b, if your second derivative is positive, you're concave up, and if your second derivative is negative, you're concave down. And that's a basic premise behind the concavity test. It's kind of like when you go to the dentist. No, not that concavity test. Okay, finding inflection points and intervals of concavity. So inflection points will occur wherever the second derivative changes sign. So on this particular graph that we've got here, all these points that I'm circling, A, B, C, or sorry, B, C, D, P, and even this one way down here, we can see that what happens, oh, that one doesn't change, sorry. What we can see at all those points is that the concavity is changing. In here we're concave down, in here we're concave up, and then on this little section we're concave down again, and then the cave faces up. And this is not really an inflection point here because we're still concave up on the other side of it. And then on the very end here, we're concave down again. So what's happening is we're actually inflecting in all those different places. So the way that we come up with the values for those is we investigate where the second derivative is either equal to 0 or where it's undefined. And even though they might not all give us inflection points, they could still be places where we change concavity. Remember, we can change concavity at an asymptote or something weird. So even though it might not really be an inflection point, it might give us something where we change concavity, and those are called, all those values where the second derivative equals 0 or is undefined are called hypercritical values. Now you don't hear that term very often, and a lot of calculus books don't even put it in there. So you probably never see that again, but if you're ever interested in it, then you sound real fancy language when you talk about having hypercritical values. Okay, so let's take a look at this example. So what they're doing here is they give us all kinds of information about a function, about its first derivative, about its second derivative, and then some limit business. And we got to put it all together and try and make a sketch of a possible graph that could fit that bill, we'll say. So the limit as x approaches negative infinity. I'm looking at the bottom here first at these limits because they're going to tell me, I can see that if they're negative and positive infinity, that'll give me some crucial stuff. That's our end behavior. So as x approaches negative infinity, we go to negative 2. And as x approaches positive infinity, we go to 0. That tells me those have got to be horizontal asymptotes. So I've got one horizontal asymptote down here somewhere at about y equals negative 2, and then I've got another right along the x-axis. So right along at y equals 0. So I'm going to label those real quickly. And notice that I'm not using broken lines here. And we've talked about that before if you've seen earlier videos. But we're not using broken lines. I'm using consistency with the way it's done in your textbook, which just uses a different color line for your asymptotes. But probably on a test or an exam, it's a good idea to draw those as broken lines. Okay, so then we're told that from number 1 up here that the derivative is positive up until we get to x equals 1, so right there. So to the left of that, the derivative is positive, and then to the right of that, the derivative is negative, which tells us that the graph has got to be increasing everywhere to the left of that. So all over this way, the graph is going up, and then everywhere to the right of 1, the graph has got to be coming back down. Okay, and then they tell us some information about the second derivative, which indicates some deals about concavity here. And it looks like, based on what we can see here, that at -2 and +2, that's where we're going to get our shifts in concavity, because we're going to be concave up outside that interval, and we're concave down on that interval. So we've got to figure out a way to make all that happen and make it all happen just on one graph. Okay, so I'm going to take a stab in the dark and say that we're going to approach the bottom asymptote as we go to -infinity this way. So that's what it tells us. So it's got to be going this way. And I don't want to be underneath that, because then I'm going to have to change, because my graph would actually be decreasing if I have to be underneath that. So that's not going to be any good to me. Then it says at -2, oh boy, I'm going to have to fix that up in a hurry. It says that at -2, I actually have a shift in my concavity. So let's get rid of that one. I got to put that in there a little better. So I'm going to have to draw my curve so that I'm increasing, going to that asymptote, and then I've got to shift concavity at -2. So right here, I've got to have kind of a bend in my graph, like that wobble you saw when you shake it back and forth. So I've got that happening. And then I've got to continue increasing all the way up until I get to +1, and then I'm going to start to decrease. Okay, so this graph has to continue increasing all the way up to +1. I'm allowed to cross horizontal asymptotes, remember, just not in the long run. And then I've got to decrease after that. So I'm going to say that it looks like at +1, I'm going to have a relative max. Might even be a global max here. And then I'm going to decrease, staying concave down, and then at 2 right here, I've got to shift around to be concave up. And then I've got to approach the asymptote at 0, going in the other direction. So that's a rough idea of what this is going to look like. I'm going to try to resketch it, because it looks really messy there. And I just want to make sure that I do a fairly decent job of this so that you don't get too confused with it. So I'm just going to knock some of this stuff out of here and then redo that. So bear with me for a sec now. Let's get rid of all this space junk. Alrighty, so let's redraw this now. So the idea was we have this vertex, which is usually a point that you want to know where you're hitting. So we have this vertex at 1, and then I've got an inflection down here at 2, and I've got another inflection down here somewhere around -2. Okay, so I've got to come up from this asymptote and then inflect at that point, and then go up to this vertex, stay concave down, and then inflect at that point and come down this way. Boy, I'm terrible at sketching these curves. I'm using a stylus to draw this on a little tablet, but it doesn't work out so great for my unsteady hand. But in any event, you get the idea. That's what your graph should roughly look like here. Okay, so example 2. Determine the inflection points and intervals of upward and downward concavity for that function. Okay, a little more algebraic. So first we're going to want to get our first derivative, which will be 4x minus 4x cubed. When I differentiate that, and then since we're talking about inflection, we're going to need a second derivative as well, so that'll be 4 minus 12x squared. Okay, so I've got 4 minus 12x squared. Alrighty, so I'm going to set that equal to 0 to try and find possible changes in concavity. I know I'm not going to have to worry about where it's undefined because it's polynomial. So I've got a common factor here of 4, and that's going to be outside of 1 minus 3x squared. So I don't need to keep that common factor of 4 hanging around. So I'm just going to find out where 1 minus 3x squared equals 0. So 3x squared equals 1, and x is going to be plus or minus the square root of 1/3, which we probably should rationalize. And we'll call that root 3 on 3. Okay, so when that's rationalized, then we have to find out the inflection points and intervals of upward and downward concavity for this function. So let's draw a little number line, and we'll do our concavity test here. If we draw our number line, we're going to have to plot a couple of points on it, one at negative root 3 over 3, and then one at positive root 3 over 3, and then we'll label those, and one at root 3 over 3, And so if you want to get an idea about where that really should be, because you don't really talk about numbers on a daily basis in terms of square roots, but that's about negative 0.6 and positive 0.6. Okay, so these numbers are at about negative 0.6 and positive 0.6. Okay, so that's roughly where we are. So then what we have to do is determine what's going on with our concavity business by testing the value of our second derivative on each of the intervals that breaks the world into. So I'm going to jump at that interval in the center right away because at 0 I'm happy. If I fill in 0 for x here, I get a positive 4. So I know that my second derivative is positive in here. So negative 1 would be outside that on the left. So if I plug a negative 1 into my equation, I get 4 minus 12, which is negative. And if I put a positive 1 in there, I get the same thing, 4 minus 12, which is also negative. So that tells me that my function is concave down, and then it's concave up, and then it's concave down again. Okay, so the only thing that remains to be seen is what are the y-coordinates at our two inflection points. Okay, so let's find those. So I've got to find f of negative root 3 over 3 and f of positive root 3 over 3 so that I can get my inflection points here, assuming that these are going to exist, and since it's polynomial, we will assume they do. And so all I'm going to do is plug those in, and using a calculator for finding numbers like this is a good idea. So let's see now. Okay, so when I plug those into my calculator, I'm getting answers of 23 over 9 and 23 over 9, which makes sense that they're the same answer because one's positive and one's negative. They're both raised to even powers here. Okay, so that's good. So it turns out that those are my two inflection points right there, and I can see my intervals of concavity, so I should write those out in interval notation. So we're going to be concave up on an interval that goes from minus root 3 over 3 up to positive root 3 over 3. And we're going to be concave down on an interval that starts at minus infinity, goes all the way up to negative root 3 over 3, disappears, and then rejoins another interval that starts at positive root 3 over 3, and zips off to infinity and beyond. Okay, so those are our intervals of concavity as well as our inflection points for that particular function. Okay, so here's the OR term problem. It says determine the intervals of upward and downward concavity for the given function. So the only thing you don't really have to do there is find the y-coordinates of your inflection points. But it is polynomial, just written in a funny form. Probably wouldn't expand it all out if I were you to take those derivatives. Okay, so have a crack at that. You want to pause the video or whatever way you like to do that, and here's the solution. So it's all worked out in its gory details for you there. And the intervals of concavity are given for you down here, and they're given as approximate values instead of all those funny square roots. Thought this was a bit cumbersome to write down in those things. Okay, and we'll just take a quick look at all the stuff that we talked about today. We said we find inflection points by looking for values of x for which the second derivative is 0 or undefined. We then evaluate the original function at each of these values to get the y-coordinates of those inflection points. And we find the intervals of upward and downward concavity by using a concavity test on all intervals between the possible inflection points, which we call hypercritical values. Fun word for the day. Alrighty, good luck with your studying. See you next time.